Okay, so thank you everyone for being here and welcome to today's seminar. On this occasion, we have Anais Möller, who is a junior at Swinburne University of Technology. And the title of her talk is Illuminating the Dark Universe with Transients in the Rubin Era. So please go ahead whenever you feel ready.
Yes, good morning and good evening, everybody. I'm coming here from Australia, where it's the next day, so it's the future. And today I'm gonna tell you a little bit about type 1a supernova cosmology and how are we measuring dark energy and what's next for us. Just a disclaimer, if you haven't heard, I speak Spanish. So if you have a question that you don't know how to say in English or want to ask in Spanish, I'm more than happy to do so. Um, Can you see my screen without any interference? Cool. Okay, excellent. Before I'm going to start here in Australia, we usually acknowledge the traditional owners of the lands where we are standing. In my case, it's the Wurundjeri people of the Kulin Nation. So Australia has different nations that have been here. It's the longest long-standing civilization in Earth, and it's incredible. And they have done also a lot of work in astronomy, and probably we didn't hear about it. For example, one interesting thing that I find, it's more like an anecdote than anything else, is constellations here include dark patches of the sky instead of stars. So they have a whole different system of astronomical knowledge. I'm currently at Swinburne University of Technology. So I work here, I'm a senior lecturer, but I'm also a DECRA fellow. And I'm gonna tell you as well some of the research that I'm doing within the Think collaboration and OSCRAF, which is a Center of Excellence for Gravitational Wave Discovery, which is not exactly type 1a supernova cosmology, but I'll mention a couple of things that we're doing thinking about cosmology or thinking about the astrophysics of these extreme physics. So to start, I'm going to start with what are transients. The sky has many different things changing, and you can find variable stars and things like black holes emitting light. But I'm interested in emissions that are transients, that happen once and then fade away forever. So for example, here we're seeing that 1A supernova exploding. Is two stars, a white dwarf star that accretes material from another one till it reaches a limit and explodes. And here I am showing two neutron stars. What you see in blue are the ripples of gravitational wave, but when they merge, they are actually emitting a kilonova, which shines for a couple of days and then fades away. So my talk will be basically centered around transients, which are observable from minutes to weeks to months. And I will tell you mostly about the optical, but I will tell you as well some of the connections with other wavelengths that we're working on. So why do we care about transients, aside from the very extreme physics that they have that we cannot reproduce on Earth? Well, here I'm showing you a periodic table of the elements found on Earth. And you can see the progenitors on the top. You have some coming from the Big Bang, like hydrogen. But then you can see that core collapse supernova, that 1A supernova, and kilonova are really basically the chemical enrichers of our universe. And we wouldn't be here without it. A lot of people that works with galaxy evolution, and this is a simulation of a galaxy evolution, and this is over mega years, so nothing that we can see in our time. You can see that all these blobs are explosions of supernova that are enriching the interstellar medium with heavy elements. Everything higher than helium is heavy. And putting those winds and making some turbulence in the galaxy formation. My main research is centered around type 1A supernova. These are basically stellar explosions, and here I'm going to show you a little video of a star exploding in a galaxy. You can see it shines brightly for some weeks and then fades away. What is interesting of type 1A supernova is, well, it's a subtype of supernova. They're super bright, So that means that we can see them far away with our imaging. So usually up to redshift 1.2 in the optical. But what's important with them is that they have homogeneous spectral and photometric properties, which is a fancy way of saying we kind of know how bright they shine when they explode, which means that we can use them to measure distances. So think about it as a light bulb. If you know how many watts a light bulb has, and you have a companion light bulb that has the same watts, it doesn't matter where you put it in the universe because you know how bright they are. When you observe them, you can know that the one that looks fainter is the one that's further away. And we have physics to describe this. Um, Taiwanese supernovae are very rare. So if you think about a standard or standardizable astrophysical objects are extremely rare. We have some variable stars close by, like Cepheids that you may have heard. Very close by, we measure distances with parallax, but far away in the universe where we're probing dark energy content, it's not, there's not many objects, and Taiwanese supernova are the most precise and have been used as a direct measurement of the cosmic expansion since the 1990s. So basically, we're going through this evolution of measuring the cosmic expansion with type 1a supernova. And what I'm showing you here, which doesn't have axis in the X, is basically a timeline. So in the 1990s, two teams asked themselves if they could measure with type 1a supernova, what is the curvature of the universe and how is the universe expanding? At that time, what was expected was that the universe was expanding, but slowing down. And what they found is, well, the curvature is flat, but that the universe was expanding in an accelerated fashion. And this is what pointed out to the evidence of dark energy. We needed to add that cosmological constant, that lambda, into the equations to make work the theory with the observations. So in that time, they used tens of type 1a supernova. So they were limited by statistical errors. Basically, they didn't have enough. And it was a starting measurement. Second generation surveys like SNLS and STSS, so it's the Supernova Legacy Survey, started going in the 2000s. I was part of one of them. So it was in the Canada-France-Hawaii telescope in Hawaii. And we got hundreds of supernova. And we measure again how is the universe expanding, and we were really measuring a cosmological constant. Now, this era starts the era of precision cosmology. We're not anymore limited by statistical errors, we're limited by systematic errors. And I'll talk a lot about systematic errors today because there has been a lot of effort trying to reduce them. Statistical can be reduced by increasing our numbers. Systematics can be only reduced by really understanding our sample, the methods that we take it, correlations, etc. Now, third generation surveys like the Dark Energy Survey happening also in the 2000s, like almost a decade apart, the observations. And our goal was to test again how the universe is expanding, but also we started having thousands of supernova that can allow us to constrain whether really dark energy is a constant or not. And I'm going to present mostly a lot of results from the Dark Energy Survey, which are the newest one, the most recent we published in January this year. And of course, the most exciting thing happening in Chile is the Vera C. Rubin Observatory coming online. Hopefully in January, we will have the first images. And we have been doing projections on what we can do with type 1a supernova cosmology for with the Rubin Observatory. Now, going back to the Dark Energy Survey. So the Dark Energy Survey had the goal of really measuring dark energy, but using 5 different probes: galaxy clustering, with lensing, large-scale structure, and Type 1a supernova. I'm just going to talk about the Type 1a supernova survey because we were really very different in the way that we work. It was a 5-year survey, so we got data for 5 years. And this is an image of NGC 253, and we're not looking for type 1a supernova there. We're looking for supernova in a galaxy like this, and here on the bottom right, it's a supernova exploding. So you will tell me, Anais, there are like 5 pixels there. Can you really do precision cosmology with this? And yes, we can. And we have developed a lot of methods to actually harness the power of the dark energy survey. So I did some simulations, and we expected at the end, once we ran the survey and we could correct for all the problems that we have with weather, etc., we expected to be detected good quality Type 1a supernova around 2000, okay? Depending on some parameters on the simulation. So the dark energy survey basically is an imaging survey, like Rubin. We just take images in 4 different band passes or filters, GRIZ, which is basically covering the optical to the very near infrared, not very far away. And what we did was take those images every 4 days, so we would have a time series. And today I'm going to tell you a lot about light curves. Light curves is basically the flux or magnitude evolution as a function of time. Type 1a supernova are very distinctive through this. So you can see that it rises and fades away. And then to complement the dark energy survey, we did in Australia during my first postdoc, so this was a while ago, the OSDES. It has a kangaroo, so clearly Australian. So we have a telescope here that is a 2 square degree field as well, but has a multi-fiber spectrograph, that's the AAT with 2DF A omega. And we took a spectra of the host galaxy and spectra from the supernova if it was still bright enough while our observing program was going. That's a limitation. Usually, to take the spectra, you need to have it like really around the peak of brightness so you can get enough photons to get a good signal to noise. With that spectra, we select supernova. Supernova come in different flavors or types. Core collapse supernova have a lot of them, 1B, 1C, 2Ps, 2s, etc. But type 1A supernova, the normal ones, not the peculiars, are the ones that we use for cosmology. So what we do is we take that spectra and we classify them, and we selected 400 type 1A supernova. And this was something that we published in 2018. And with this data set, we did what we call a Hubble diagram. So let me take you through this. So a Hubble diagram is a way that we measure how the universe is expanding. Usually is a distance modulus, which is a luminosity distance, versus redshift. So all the yellow and red points that you see here are type 1a supernova. And what we do is that we compare those observations with different models. And here you can see the models with, especially in the bottom, because you can see the residual. Can you see my mouse, by the way? I don't know. Let me see if I can see somebody.
I don't think so.
Can you see my mouse?
No.
No.
Okay. So I'm gonna tell you by moving my hands and telling you what to look for. So the bottom panel has the residual of the difference between the luminosity distance measured and the theoretical one. For example, here is lambda CDM, lambda for cosmological constant, CDM for cold dark matter. And here we can see that clearly we are agreeing with 30% matter, almost 70% dark energy. So we really need dark energy to explain these observations. Now I'm gonna dig a tiny bit, because you're a cosmology group, into what it means, the distance modulus, in case if you want to see the theory behind it. So the whole idea is that you have a luminosity distance, which is basically a measurement of the brightness of the type 1a supernova. And we compute what we call the distance modulus, which is mu, which is a log scale of that. And that luminosity distance is related to the content of the universe in matter, dark energy, etc. And you can write it like this. And most of the time we talk about dark energy as a constant, which would mean this equation of state means -1. And this is what we have been measuring during in the 1990s when they found the first measurements, SNLS and the Dark Energy Survey for 3 years. We have been really measuring whether it's -1 or not because we couldn't go a little bit further and say, what about if we parameterize this W as something that is a constant plus something that is changing with the cosmic scale factor, which is WA. But until now, we haven't had the power to really constrain WA W0. We have been only searching for the part that is constant. So for the first 3 years of the Dark Energy Survey with these 400 type 1a supernova, we constrain omega lambda against omega matter. So basically to see the proportion of the content of dark energy, dark matter in our universe. Very what we call vanilla, very what we expected. We were really consistent with what the CMB by itself or BAO by itself was showing. You can see that here we still plot accelerating universes, and flat universe. So you can see where the constraints are. And then if we measure the equation of a state, we really are in that -1, that is the cosmological constant. Okay, so these are the results for the first 3 years of data. I remind you, we had 5 years of data in Dark Energy Survey. We published this in 2019. So well, already we have 3 years of data. We have shown the power of the survey. How can we scale this to the next analysis with a full data set? So there are three main things that I'm going to talk about here. I highlight them in different colors. Standardization. So how do you get that distance modulus from the type 1a supernova? I'll tell you more about it. In green is how do you classify and select those type 1a supernova? Because I told you that we are in precision cosmology, so systematics is a big thing. So we need to understand how we select them. And in purple, measurements of redshift. So these are three big areas that we can improve our data set. And if you go more in detail, and if you see, and all these cosmology papers have this, is that we have a budget of our uncertainties. So here is the uncertainties of our analysis. You can see that we're dominated by systematics, and the main four groups are photometry and calibration, so the low redshift sample, the sample that is closer to us, because a smaller volume, less type 1a supernova, more biases, and also come from other surveys. Calibration, then you have selection effects, which are in green, which is basically efficiency of selection. How do you detect, gather that sample? And in yellow, you have things like understanding how the type 1a supernova are, like the populations, their properties, how do we measure those distances? And in purple is the redshift. Now, I'm going to talk about the green one and the yellow one, but if you have any questions about the blue one and the purple one, please let me know. But then the seminar will become a longer thing if I went through all of them one by one. So let's start with classifying type 1a supernova because it has been one of the focus of my job for a long time. I told you that we were classifying with the spectra, and that limits because we need to catch them when they're shining brightly. Also, sometimes we don't have telescope time to get them while they are shining. It introduces selection effects, which is one of our major constraints in cosmology. So a way to classify as well is photometric classification. So this is kind of new. We started doing this 10 years ago. And nobody believed we could do cosmology with it because the idea is that we get partial information, which is basically that light curve photometry flux against time, and classify the different types of supernova. And close by, you can see the difference, but further away, it starts to be kind of complicated. So for a long time, people didn't believe that we can get to a level of contamination of less than 2% to be able to do cosmology. But I'm going to tell you how we overcome that. And again, this is partial information. spectra gives you so much richer information that can help you really see the absorption lines of the supernova. So I developed in 2019 a package called Supernova. It's a deep learning photometric classification network framework. The idea is that you introduce fluxes and times in the different band passes, and you will get out a probability of this time series being a type 1a supernova or not over time. Um, and when I developed it, the idea was to do cosmology. So special emphasis on accuracy, also classification at any time step. I'll tell you a little bit about that later, but also statistical robustness. So this worked very well in simulations when I created it. But the question is, can we use them for cosmology? And Maria Vincenzi led an amazing work that we should have called it Let's Try to Break Supernova, because basically that's what we did. We tried to break it. So we changed the simulations we trained. We changed the noise. We changed the templates of the core collapse and type 1a supernova. We changed a lot of things and tried to see if we could still maintain a contamination that was less than 2%. And what you're seeing here is the number of percentage of core collapse supernova, which is our contamination as a function of redshift. And we tried different methods. Everything that is red and yellow is supernova, and in blue and purple is chauvinet, which is basically like a sigma clipping. Okay? And you can see that we really can contain that contamination almost flat over redshift with a very low level. So, and we also show that it reduces biases. We have less selection effects. We're selecting more type 1a supernova, so that means better for cosmology. So Maria did this paper with simulations, and then I was like, okay, let's do this with the data. So here are some of the beautiful light curves of the dark energy survey. We use also host galaxy redshifts as an input, as a feature to supernova, and we got 14,000 type 1a supernova. This is the largest sample cosmology grade that we have had from a single survey at high redshift. Just an example how powerful this is. In brown or red, I am showing the spectroscopic sample, and in yellow, I'm showing the type 1a supernova that we classify. And you can see the redshift distribution. We're really pushing further in redshift. We're really getting most of our sample there. So this was pretty exciting, and now let's do cosmology with it. So this is a Hubble diagram that we just published this year. Daniela, you have a question?
Hi, yes.
Yeah.
I wasn't sure if we can ask questions during the talk. So
It's okay. Yes, you can ask.
so my question is, all the supernovas you show from photometry are confirmed as supernova 1A, or there's some probability or any uncertainties on if they are supernova 1A, yes or no?
Yeah, so these are all photometrically classified. So we have this probability of being type 1a supernova. So we have studied where the threshold should be to be sure that it's a type 1a supernova. From the
Okay.
1400, a subsample is a spectroscopic sample. So the 400 that we really know are there. So we can compare with that, but as always, we cannot have spectra for everything. And this was done afterwards, so we don't have all of them. So that's the idea. We take something that we know, we do a new method, we test it with the simulations and what we know, and then we extrapolate it to the rest of the sample.
And okay, thanks. Okay, that answers my question, but I have another question. So what would be the object that confuses the most the algorithm? Like supernova 1A looks similar to another kind of supernovae or other transient?
Yes. So with full light curves is type 1A versus 1BCs. So these are a subtype of core collapse supernova. This is especially looking so type 1A supernova, very high redshift, looks like 1BC at closer redshift. So adding redshift breaks the degeneracy a little bit, so we can get the contamination very, very low.
Mhm. Okay, thank
Yeah.
you.
But if you're interested in contaminants, I'm more than happy to talk about their characterization. I
Okay,
think there's another hand. Domenico. Domenico?
Hi. Now, yeah, Domenico.
Sorry,
Hi.
Domenico.
So now the next question. Okay, so you said just to get because I don't know. So the photometric are much more, of course, but they're more uncertain because okay, they mix confused with type 1b is a supernova, right? So, but it's the shape. Just a question. No, it's the shape that changes, or also the measurement, the error on measurement of redshift that it's a problem because I don't know the.
So it's here we're dominated is by the shape of the light curve. So actually, let me go to the Hubble diagram already. So here I'm showing in blue all the dark energy survey supernova. This is without saying this is a type 1a or not a type 1a. Be careful. This is a little bit different. And what we did is that we weighted our analysis by the probability of it being type 1a supernova. So you can see if you measure the distance modulus with things that are clear blue, they are way outside the measurement that we're searching for. Why? Because type 1b's and 1c supernova are not standardizable in the same way that type 1a supernova are. So clearly those would have been caught if we do like a sigma clipping. What worries me is the ones that are really where our measurement is. And you can see a couple of them, especially at redshift 0.5. And those are the ones that the machine learning algorithm has been trained specifically to get out. So if you did sigma clipping that I showed here, you can see that our contamination goes up and down. But if you do the machine learning algorithm, and we train it really to do this, it will lower that contamination to less than 2% throughout redshifts.
Okay.
Does this answer your question?
Yes, thanks. Thank you so much.
Perfect. So yes, this is a new way of doing cosmology with a photometrically classified sample. When I did my PhD a long time ago, nobody believed we could do this, but we have really tried and tested this. And we're very proud of this Hubble diagram because really the measurement is pristine. We're really doing a different type of analysis weighting with these probabilities, and we can show that it's quite robust actually. What's interesting about these results is that if you see flat lambda CDM in purple and you see flat W0, WA, CDM, you can see that they are quite close. And we're starting to get that power that we can disentangle between these two models, finally with type 1a supernova. So this is like a new era for us as cosmologists. We finally have that power. So I'm showing again W, the equation of state of dark energy, as a constant against omega matter. And the first thing that you will see is that our contours are not exactly -1 anymore. So we're seeing that there is a small shift of W, and that W has implications on things of the age of the universe, for example, if it's true. And you can see that we are more consistent with something that is -0.8 than -1. So this is the first tension that we see with these results. Of course, this is 2 sigma consistent with a cosmological constant. We're not claiming that we have found and discovered this because in cosmology we need 5 sigma and we need also verification of other groups. But then we start measuring what about a constant W0 and a factor that changes with the scale factor of the universe, WA. And you can start seeing that we are not in WA0, which would be a cosmological constant, where actually our tension is going away from that and saying that we have hints, and we call this tantalizing evidence, that WA might not be 0. So a dark energy that is evolving with cosmic time. Now, again, this is not a 5 sigma result. This is a hint, but this got us very excited. Why? Because we are really trying to push this analysis to understand something a little bit different from previous analysis that is getting that WA. Now, to give you a little bit of certainty on how thorough we are, I'm going to show you our error budget. This is our error budget. There's a lot of colors. We couldn't find any more colors or shapes anymore to put it here. But you see the same families that I showed you before. We have in blue calibrations. We have in orange everything that is about how we standardize measurements, and I'll go through that next. And then classifiers is in green. So what we did is supernova was used for the probabilities, but to test whether there was a problem with the classifier or the training or the architecture or anything, we applied other classifiers. We put a prior. We did a lot of things. And you can see that there are systematic uncertainties that are tiny. Like classification is not our dominant systematic. So this is pretty amazing. The other thing that is very important here is that we're not anymore systematics dominated. We're back again statistics dominated. So, which means more type 1a supernova will reduce these error bars again of the measurement. So this is a new era for cosmology. So it's pretty exciting. So now I'm gonna go towards what are we doing now that we have published this 5-year result to standardize type 1a supernova. So when I showed you what are type 1a supernova, I told you, well, a carbon-oxygen white dwarf that you see here in blue, and a companion star, carbon-oxygen white dwarf, its material explodes at the Chandrasekhar mass, but that was like a Disneyland story. We have evidence now that we may have different channels of progenitors. So a carbon-oxygen white dwarf with another white dwarf, with a red giant, with a main sequence star. We have also shown evidence that it can be Chandrasekhar mass, sub-Chandrasekhar mass, or super Chandrasekhar mass. So basically, there are some variations in type 1a supernova that will affect the standardization. So the focus here is we have these very large samples. Let's study the properties of the type 1a supernova to have a better standardization. So how do we get that distance models I was telling you about? So if type 1a supernova were perfect standard candles, what you would do was you compare what you observe in a B band, so basically a wavelength, and you compare it to the absolute magnitude, the magnitude that it exploded, okay? But since the 90s, we know that that's not true. Type 1a supernova are standardizable candles, not standard candles. We need to add some corrections. So the first correction is what we call the trip relation. So until there, it's the 1990s analysis. Basically is adding some correlations that we find with X1, which is what we call a stretch, how wide the light curve is, and color, the color of the light curve. So that's X1 and C. Alpha and beta are constants, and this is the trip relation. So in the 2000s, we started finding that we had another correlation, that is this G host that you see here. We see that there is a change between the brightness of supernova in different galaxies, and we correlate that with host galaxy mass. And in blue, you have selection effects because you have things like Mankey's bias and other types of selection effects. Basically, the further you look in redshift, you are biased towards brighter things. So let's say that you have apples that are very bright and less bright close by, and apples that are very bright only far away, and you want to do an analysis, you need to account that these very far away apples are not having the whole population of apples, because those populations are also correlated with stretch and color. So I spent a lot of time in cosmology working in selection effects. That was one of the first things I did as I entered into the dark energy survey. And one of the ways that we can test all of these is, aside from simulations, is to be a little bit creative. And here I'm showing you a plot with 3 different samples. This is all data from the dark energy survey. In this case, the purple is the spectroscopically classified type 1a supernova. In orange is the sample that we use for cosmology, and that uses host galaxy redshifts. And in green is a sample that I created that has larger contamination. This is a disclaimer, but it's a sample that I created without any host galaxy information, which means we can get things that are hostless, we can get things that are too faint, maybe to get the host spectrum. And here I'm showing you the distributions of the peak magnitude in the I-band for the supernova and the host magnitude. And you can see that we can test selection effects by seeing, well, if I had a complete sample, let's say that this is complete, how will this distribution look like? Where am I starting to get less type 1a supernova? And we did this with simulations. But if you have worked with simulations and data, we all know that simulations are great, but data has other challenges. So this green sample is something I published this year. It's a sample that is almost complete, 2,300 type 1a supernova from the Dark Energy Survey. And one of the things that we tested was to see if we can see any evolution of those color and stretch factors that we use for standardization. Are they evolving with cosmic time? And that will have to change our results, you know. And in gray and red, I'm showing you the simulations, and in black, the measurements, and you can see it agrees. Mostly there are some tension, some parts, and we're working on that, but it agrees mostly. So we're really understanding that our data and simulations are not very far from each other. One of the things that I'm working, I have a student working on this here in Australia, is why are type 1a supernova brightness correlated with host galaxy mass? So can it be selection effects? Can it be the progenitor channel? Some higher mass galaxies have more this type of stars than others. Can it be the dust content on the galaxy? So you can see here what we call the mass step, which is basically galaxies that have less than 10 here in the vertical axis in red or orange. I don't know which color is that. You can see that it's a little bit different. There is a step here. So one of the things that I did was to try to get these with the different samples I showed you, spectroscopic, the cosmology sample, and a sample that has no information on the host. And you can see that the mass step is actually a little bit reduced as we go to a sample that has less problems with the host galaxy redshift. This is not a final result, but this is something that we're investigating. And here in Australia, we have also been taking spectra of the host galaxies to try to see if we can find markers like metallicity or star forming ratio indicators that can help us understand this mass step. A lot of people will tell you it's dust. We haven't found evidence that it's actually dust using two spectral lines of galaxies, but this is something that we're working right now. So in bottom line, we have done an amazing analysis with a new type of technique. It has been thoroughly validated. We have some evidence that there can be an evolution of dark energy with cosmic time. And later this year, DESI, and this is, they published in April, but these ones I got from the paper from this week, they showed this result. DESI is basically a spectroscopic survey in the Northern Hemisphere using galaxies, basically not using supernova. And they are also finding evidence for an evolving cosmic time dark energy. So this is by themselves, and you can see it using old type 1a supernova samples like Pantheon and Union, or even with our sample, you can see that this is also very relevant. So this is still not a 5 sigma either, but this is very exciting times. So in the next part of the talk, I'm going to tell you a little bit about Rubin and how we can actually extend this analysis to Rubin. You're in Chile, so you probably have heard about Rubin a lot of times. Amazing telescope, world's largest CCD camera, a 9.6 square degree field. with a 10-year survey starting next year, covering this beautiful southern hemisphere sky. In yellow, you see the deep drilling fields where we expect thousands of visits at the end of 10 years and hundreds of visits in the full southern hemisphere. This is amazing. I'm in the southern hemisphere, so we are looking forward to having that data so deep, because we're going to get with a single exposure of 30 seconds up to magnitude 24. So a different from SCSS image to LSST like here, showing on the right. So my main research right now is working on one of the data products that is not proprietary. I know in Chile you have access to the proprietary data, but the data from transients, which is every time you take an image in Rubin, you will do an image subtraction, which is basically you take the observation, you subtract a template, and that blob of difference of something changing in the sky will be publicly available, and that light curve brightness evolution will be publicly available. But Rubin expects up to 10 million detections per night. And that's basically this. We have a very big wave of alerts, and maybe we want the 1 million supernova 1A that is in this beautiful wave. It's a great opportunity to constrain dark energy and do other exciting science, but how can we get to select the little amount of data we want? Because we don't have petabytes of data in every house to copy all of Rubin data. So that's what Think is. Think is a broker. It's a broad science collaboration that I'm leading together with Julian Peloton and Emily Shida, that both work in France. Julian is French, Emily is Brazilian, so another South American in the team. But we're in international collaboration with 70 members in 14 countries. You probably have heard about brokers before because you have one of your own in Chile, in El Erce, led by Guillermo Cabrera and Francisco Foster. So we're 7 around the world that have data access to those 10 million time domain candidates per night in real time, every night for the next decade. Regarding Think, well, we were part of Operation Rehearsal this year in June. Basically, they simulated 9 million detections, and they took the data from the telescope to the data processing center in the US and then sent it to the brokers that wanted to participate. And we tested our infrastructure to see if we could handle that data, and we can, and we are ready. So this is pretty exciting. So basically, Think is a collaboration, but we're also data access to those millions of measurements. And one of the things that we do is that we're really broad science collaboration. So I have been telling you about type 1A supernova because those are the ones that I have been working with mostly during the last years. But we have people experts in asteroids, AGNs, microlensing event, satellite debris, etc. So to give you a little bit of an idea of how a broker works, if you haven't heard about this, we basically, what we do is that we get that data. In Think, we don't have any hierarchy. So basically, every alert that is not noise gets processed, which is 70% of them. The first thing is that we cross-match with catalogs to know if this is something known, if it's in a host galaxy. Then we cross-match as well with gravitational wave footprints or neutrinos or gamma ray burst footprints from other surveys. And then all of these alerts get a score of machine learning classification. So of course we have type 1A supernova, because then I wouldn't be leading the collaboration, but we have other things like fast transients like kilonova, microlensing events, and other types, periodic, non-periodic, AGN, etc. And then the users, you or the community, can decide a customizable filtering, saying, look, I want things that are rising in galaxies that are blue and that has this probability of being a kilonova, for example. And then you can access it through ways. One of them is a real-time API. So for example, I have a project connecting for automated follow-up here in Australia for Rubin targets. So that's great because When the night finishes in Chile, we are starting our night in Australia, so we can follow up spectroscopically and photometrically some of the interesting targets without me staying awake at night. I appreciate sleep. So this is all robotic. But on the other side, if you want to Google thinkportal.org, you can go and right now look at the CTF data that we're using as a precursor for Rubin. Of course, there's much more than I can tell you today. It's a community. These are some of the events we had. We had one in South America. Actually, Guillermo, somewhere in this picture, Guillermo came to Brazil for the Think Brazil meeting. So although brokers, people say we're competitors, we're actually quite close, especially with Alerce. So we share a lot of our events. So if you see in the picture, probably somewhere there, I don't know where, but probably he's somewhere there. But he's not a member of Think, but we are working together in infrastructure and trying to make things better. We have a lot of science cases, from supernova to AGNs. I am working with like radio data here in Australia. We have an agreement with Euclid for solar system objects. We have a connection with gamma ray burst space telescope like SVOM. So the idea is this is community driven. Basically, we want more people to do very different things like microlensing and things like that I have never touched in my life. So the idea is to maximize science. And I'm going to tell you a little bit about what we're doing for Type 1a supernova, and then I'll close up and we can discuss more. This is part of my work in the Dark Energy Science collaboration, but also with Think. We are seeing that the photometric classification is really becoming a standard. Amalgam, which I am not part of, which is analysis of pan-stars and SDSS, they use supernova to actually do a Hubble diagram as well and do a cosmological analysis. So this is really becoming something very extended in the community. We are also developing Type 1a supernova classifiers with simulations. Elastic, which was a simulation for LSST, that you can see the results here on the confusion matrix of Type 1a supernova versus other types for LSST-likers. And on the right, you have some work that we have been doing to measure rates of Type 1a supernova using simulations from LSST. But one of the things that I am most intrigued about is Type 1a supernova and early Type 1a supernova. So when they're really rising, you know? Why? Because this is where we really don't understand Type 1a supernova. This is where we can have evidence of that companion star, because there can be shocks in the atmosphere of the other one. Our models are not complete there. So I have been working in Think to select very early Type 1a supernova. We are reporting them to the transient name server publicly, but we also have a program here in Australia to follow them up spectroscopically. And if they are deemed to be very early, we also follow them up in Chile in the Blanco telescope with DCAM, so we can improve our models of Type 1a supernova. So the challenge here is that instead of having that whole light curve with tens of points, you may have like a handful. So the challenge is, can you be accurate with this? And it's harder. You cannot have 2% contamination. You will have much more. But you can see, and this is with real data, this is not with simulations. You can see that most of them, 80% here, are Type 1a supernova, even if you're selecting with 3 to 6 measurements. So this is pretty interesting. We're really working, if you have machine learning people here, I'm gonna just give you a glimpse of something that we're working right now, and I'm gonna publish that probably beginning next year because it's the end of the year. Usually supervised learning, you use a training set of known events or a simulation to train an algorithm. You apply that algorithm to known events and you select the best to get your sample. We have been working on doing active learning, which is you select the most unsure and you get those labels to try to improve your classifier. and I did a program the last 2 years here in Australia. And we have been showing that we can really optimize how follow-up is done to get really better type 1a supernova samples very early. But that's something that I haven't published yet, so I won't show the results yet, but will be soon online. I think I'm running out of time, Vicente, no?
I mean, you can have 5 minutes, I think, in order to have some
Okay.
questions at the end.
Yeah, sure.
Yeah.
I'll just mention this. I won't go into detail. We can do much more than that. We can do more than type 1a supernova. We can study the supernova. We can do kilonova. If you want to see some of the other science cases with transients, we did a science roadmap for the transient and variable star collaboration from LSST. You can take a look at it. But I'm going to mention one thing, that is, there is way much more than supernova. And this is a cartoon, literally a cartoon. The classes are not rounded or square. The magnitude against time indicates there are so many things that we don't know, and these are some of the things that I'm interested on, and some of my students are working with. You can see a type 1 supernova tiny there in purple. But one of the things that is very interesting about this decade is that not only we will have Rubin giving us insights on all of these, but we also have so many multi-wavelengths surveys doing that. And here in Australia, we have ASCAP, which is a precursor of SKA, and I'm working with them to try to haze this with FINC. But we also have gamma rays and Roman coming online, etc. So one of the things I'm interested on is kilonove. In 2017, I have been moved a lot, but it was my first time in Australia. And I led one of the projects that was a sky mapper, and we got images of the first kilonova ever detected with gravitational waves and gamma ray bursts. Of course, we haven't found any. You probably know that that we have all this detection abundance of data, because how it works is that we usually get a gravitational wave trigger. We search for a counterpart in the optical or electromagnetic, and then we find the kilonova. And we expect with Rubin to have around 10 neutron star mergers per year, which will give us a kilonova. Let's see, because the rates are evolving still. And you can see we did some projections about that, but we expect to have 300 out to 1,400 megaparsecs. And one of those things that we can do, and we are doing right now, is trying to find them without the gravitational wave detector, because you need a direct, like you need that it's close by. There's a lot of things that you need to do. And we have been working with GRAMA, which is a global network of telescopes. They actually have telescopes in Chile. And we have been trying to find kilonova. We haven't. If not, this will be like a Nature paper and not like the last slide of my presentation. We're just finding a lot of CVs, some asteroids, some supernova. But this is very interesting because we're trying to see if we can find more kilonova and characterize them. So I'm gonna finish then. Today I have told you a lot about dark energy survey, how we have the tightest constraints on dark energy from supernova to date. How do we have hints of dark energy evolving with time? How we have changed the analysis to become something more robust with more control of the systematics. We are working towards Rubin, in particular with FINC. We're trying to have this data set available for science, for many types of science. And I think Rubin will be an amazing opportunity. I think really we're going to be able to constrain in the next years whether dark energy is a constant or not, and discover extreme physics of transients that we haven't thought about. So I will stop, and if you have any other questions, I'm more than happy to answer them.
Thank you very much, Anais. I don't know if anyone has any questions. I have a couple, but Domenico.
Hi, thank you so much for the very nice talk, actually. And now, curiosity about Vera Rubins. Do you know, because at some point, I mean, I remember that one of the forecast paper, they said that the Rubin will release or they intend to release a catalog with something like 9,000 supernova. They expect to have 9,000 supernova. Do you have any new number? I'm talking about like, I think 2 or 3 years ago I read this. I don't know if it is still on, if the I
So,
don't know if it's a question, it's an answer. I don't know if you can answer this. I mean, but
so
yeah.
So there is a difference between the number of supernova you detect, the number of type 1a supernova you detect, and the
Yes.
number of type 1a supernova that are good for cosmology.
Yes, I'm talking
Three
about
very
those of
different numbers.
yes, yeah. No. I mean, I'm talking about the type 1 supernova that will be used for cosmology.
Yes. So,
Mm.
so the thing is that observing strategy with Rubin has changed a lot in the last 2 years. And we have gone from like thinking that we cannot do much cosmology to saying, okay, the ballpark number is around 1 million at the end of the 10-year survey.
Okay.
It will depend a little bit on the final decisions on the observing strategy. But yeah, we're talking not 2,000, we're talking much more than 2,000, like an order of magnitude, at least.
Yeah, it was like 8,000.
Yeah. So yeah, it depends a little bit on which observing strategy you're talking about. And also which redshift range are we cutting off because of the filter selection. So Rubin has the Y filter that goes a little bit more towards the near infrared. And that one is very useful for high redshift type 1a supernova, like between redshift 1 and 1.2, 1.3. There, it's very powerful, but it's very time consuming, that filter. So it has been a big discussion on that one. Yeah. So sorry, I don't have a number for you, except that it will
That's
be
fine.
like I'm guessing it will be 2 orders of magnitude higher what we have right now. Will we arrive to the 3, which is the million? I don't know. But
Okay.
yeah,
Okay, thanks.
no worries.
Daniela?
Daniela?
Hi, yes, thanks for the talk. I learned a lot. So I have a question about the contour plots, the cosmological constraints. When
The
you
new
have
ones, I'm guessing.
DSY5, the
These ones?
supernovae.
Yes.
Yes, I
Or
think you
this
should.
one.
Yeah, exactly that one. I'm
Yes.
curious because I see a tension between supernovae as CMB, right, and omega mater. And for CMB, I think also cosmic chronometers H0 and omega mater are super correlated, right? So it's the same effect we are looking at here.
So what's interesting with that 1A supernova cosmology at high redshift is we don't care about H0. H0 is a constant. It will just displace us up and down.
Exactly,
So
omega
H0
mater.
really tension doesn't enter into these results.
Mhm.
The difference between CMB measurements and that 1A supernova measurements is that they're really orthogonal in the plane. So we
Yeah.
really see very different things. Probably I should show you the all contour plot because I think it's more clear there. And you can see the CMB here in yellow. It's that way. And the type 1A supernova is that way. And you can see now with the scale, you can see how much better now supernova are. That we can see instead of a little line in CMB here, it's a big thing, you see? It's a thicker thing. So it's not the H naught that we're testing here, definitely not. Could H naught be resolved by varying dark energy with cosmic time? Yes, but the value would be so huge that we cannot explain it. So we cannot solve H naught here. And we're not measuring H naught whatsoever. So what you're seeing is the different constraints that you have, omega matter, omega lambda, no H naught whatsoever here.
Mhm. Okay.
Yeah.
Yeah, because it looks like omega matter. It's supernovae wants to have more matter in the universe, but it's not well constrained, right? So it's
Yeah.
no prior here. Okay.
It's degenerate. For us, omega matter is something that is very hard to constrain directly. Yeah.
Mm, mm.
That's why
Okay.
we combine the results. And that's why the dark energy survey, we had these 5 probes. So we can actually combine the results and then constrain better the parameter space.
Mhm.
Yeah, because here you're not seeing the CMB degeneracy. Well, in this one, you can see that CMB doesn't constrain at all this way. In the other one, it's just combined. So yeah, that's why it's misleading.
Okay. Okay. Thanks.
Yeah.
And are these results also consistent with Pantheon Plus for the parameters you're constraining?
Yes. So Pantheon Plus is a small. So Pantheon Plus includes the ES 3 years. This one that I'm showing right now. I'm
Oh,
part of that. So there has been a recent paper by F. Tansu, I never pronounced the name correctly, saying
shocking.
that there is this, the results Pantheon Plus and the ES don't make sense. The paper just got through collaboration wide review. Our answer, the answer is that no, it's just because some systematics were not explicitly said. We are consistent with Pantheon. The differences are really how the analysis was done.
Oh, okay.
Yeah.
Okay. Thank you.
So look out for the archive. We should be putting this online like in a week or two. It's literally the answer to the paper.
Okay. So that would be a paper for journal clubs then. Thank you.
Yes, it's a paper of the Dark Energy Survey showing that really there is no inconsistency between Pantheon Plus and Dark Energy Survey.
Mhm. Okay. Thank you. And thanks for the
No
talk
worries.
again.
No worries.
I have two questions, and one of them, you showed a plot about comparing your simulations with data, and you saw that this didn't agree very well. I mean, it agreed very, very well, but at high redshift, it was the difference were bigger. Do you know why do you
This
think?
one?
Yeah, yeah, that one.
Okay. What was the question?
I mean, could it be explained by some phenomenologically, or why do you think this could be at the high redshift?
So the high redshift, well, that last bean has a lot of errors. You can see the error bar is large. I wouldn't trust that last redshift bean very much. I would be more concerned about the lower redshift displays that we see a little bit. One of the things that is happening is that we're changing how we model the population properties of type 1a supernova through cosmic time, because until 10 years ago, we thought it was like the same close by and far away, but that doesn't make any sense because you have a stellar evolution. So the environments are different, the stars are different. So we have been characterizing color and stretch now with 2 distributions that are overlapped. And what we're doing with this type of plots is trying to understand if we should change how we parameterize this evolution with cosmic time. It's not a major systematic. It won't change the cosmology results. What we're seeing here is hints that we need to dig into this. Yeah, it's a good test to do to try to really understand how type 1a supernova properties evolve with cosmic time. But it's pretty
Okay.
good. Like, I'm not too worried about this. I'm more worried about the math step. That one I'm worried about.
I see, I see. And I
Yeah.
want to ask you a different question, maybe out of topic, I don't know. But do you know if with the light curves, one could build something like an image to give it to a convolutional neural network and that predict, I mean, classify maybe directly from light curves, but translating this light curve to an image that the neural network could understand? Do you know if people try to do something like this?
Yes, we have done that. I can tell you which paper to look for. It's one of the classifiers that we use in the dark energy survey to test. It's called SCONE, like the little bread, led by Helen Koo in the US. So what we did was we did an extrapolation to get the wavelength smooth, which, for example, supernova, we didn't do that because I didn't want to assume extrapolations, but in Scone we did. And we did like a soft map, a 2D image of the light curve, basically, over wavelength, and that was fed into a CNN.
Okay.
Yeah.
And is that hard to do? Or
No, you can take a look. The code is public. Scone is
okay.
public. Yeah.
Okay.
CNNs, I actually tried CNNs as well in Supernova. You can choose a CNN because it's a framework that allows you from RNNs, LSTM, GRUs, CNNs, and I have three types now of Bayesian neural networks, and you can choose which ones are you using. So I tried CNN with the time series as well. The results are a little bit worse. When you translate it to an image, the results are better. But it's a classification as well that is good for type 1A because we know type 1A a lot, but for other types, it makes it more challenging because of that extrapolation. The other one that you may be interested is Rainbow. That is Etienne Rousset. It's a way to extrapolate the light curves using some physics, like black body equation or things like that. That may be interesting if you're trying to convert light curve to an image. So it's Russell, Russell.
Okay, thank you very much. We have
No
another
worry.
from Alejandro.
Alejandro?
Hi, Anais. Can you hear me well?
Yes.
Yeah, great. And first of all, thank you for your talk. I really enjoy it. I have a question regarding the treat formula, specifically concerning these nuisance parameters.
This one.
Yes, I would like to ask if you know some reference where alpha, beta, and gamma are constrained, because in papers always say, okay, alpha, beta, and gamma have some value that appears, I don't know how, and never go so deep in those calculations. I would like to ask about a reference
So,
about those values.
from the top of my head, I don't know which is a good reference, but what I can tell you is that we fit them for every sample. So every sample has a different alpha, beta, gamma. It's not
Okay.
ridiculously different, but we fit it all because what we have is how we compute this. We get MB, X1, and C for the supernova 1A model. In this case, we're using SOL 2 or SOL 3. And then alpha, beta, gamma are fitted when we do the analysis simultaneously. It's basically
Okay.
coefficients. So you will see that in each of the sample, Pantheon Plus, DES, any of the SNLS, we have a slightly different value of alpha, beta, gamma. And it depends really on the sample. It's just a scaling. I'm trying to think if I remember somewhere where it's properly explained. I cannot recall from the top of my head, sorry.
Okay, no problem. But
That's
I
not
think
the
that
part I work on in the analysis, actually.
but if you don't mind, I will email you because I have a question more technical, so
Yeah,
regarding
no
the
worries.
supernovae.
Yeah, no
Thank you,
worries.
thank you.
Okay, so
I'm guessing you have my email. If not, it's I'll put it in.
I
Yeah,
can
it
give
was in one slide. Yeah, so right.
Yeah, maybe in the
Okay.
first one. I don't remember. Well, worst case, I'll put it here. I'll write it for you. But anyhow, Vicente should have my email.
yeah, I was going to say that I can give him the email.
Yeah.
Thank
Yes,
you.
they're on the right.
Okay, so thank you everyone for coming, and thank you, Anais, for taking the time in very early in the morning for you.
No worries.
It was a very nice talk. Thank you.
Thank you all. And yes, feel free to email me. And yeah, I miss Latin America. So